Okay, this video is about potable water questions and to go through the video explanations of the answers and how you go about prepping your questions. So first of all, I'd like you to go to https://uodyee.exampro.net, or you can just write uodyee.exampro.net. Okay? Now the first question is this. Water is important to all living organisms. It's a part of Africa. Getting people potable water may be difficult. What is potable water? So what is potable water? Now that's one thing that we spent a bit of time learning about, what potable water is. So the first thing we'd like to say is it's just simply safe to drink. So water that is safe to drink. Now, describe the role of fine sand is the second question. Well, let's have a look here. It says biosand units, one method of purifying water used in some parts of Africa. The diagram below shows biosand unit. Okay, looks like we've got contaminated water poured at the top. We've got a fine layer of bacteria there, and we've got some fine sand. Okay, and then underneath we've got gravel and coarse gravel. And then out of that comes the potable water. So describe the role of the fine sand. This is to filter the water. So it acts as the filter. Now, the next question here, a bit more information. Another method of purifying water is a solar disinfection. We call it SODIS. Okay, this table below gives some information about the methods used. Method, biosand unit, that's the one we just looked at, or SODIS. Okay, we've got a description, and then the percentage reduction in pathogens. Now this one had a 47% reduction, this one 31% reduction. Okay, before use, it needs to be left for 2 weeks for the bacteria in the unit to grow. Can treat 40 litres of water per hour made of concentrate, of concrete. Needs replacing every 10 years. Okay, you've got to replace it every 10 years. SODIS, plastic bottles are filled with water and left in the sunlight. Ultraviolet UV kills bacteria. Bottles need to be left in the sunlight for 8 hours. Okay, this one needs to be left for 2 weeks. Okay, bottles have to be replaced every 6 months. Okay, 1 litre bottle of SODIS costs 29p, and each litre bottle needs to be replaced every 6 months. We said that there, so every 6 months. A family uses 6 litres of potable water per day. Calculate the cost per year of SODIS for the family. Okay, so we need to have 29 pence, 29p. Right, we times that by 6 because they use 6 litres. 6 litres, 29 times by 6. Okay. So 1 litre bottle, it costs 29p. Each litre bottle needs, each family uses 6 litres a day. Calculate the cost per year of this. So we've got 29 times by 6. Which equals, let's get the calculator out. That's £1.74. Okay, and we need to replace that every 6 months. So we need to times that by 2 because we need to replace that every 6 months. So we times that by 2. That equals £3.48. So down here we write £3.48. Okay. Now, next question. Other than the cost give 2 advantages of using biosand unit instead of SODIS, other than the cost. Other than the cost. So you can't mention the cost. So we said give 2 disadvantages of using the biosand. So you have to wait the 6 months, wait longer for you to use the water. We have to wait longer to use the water. And then secondly, it's not very portable. And if you can remember why it's not very portable, it said that's made of concrete. Okay, so it's, you know, that's not, you can't just easily move that around. Next question. Give 2 advantages of using biosand unit instead of SODIS. So 2 advantages this time. So this time we can talk about the advantages. Well, straight away, if we have a look at it, it can do 40 litres per hour, which is really good. And the other thing is maybe it's better at doing the job. Okay, so let's say it's a better filtration rate. And it's more effective. Okay. And should we put those numbers in? Okay, it's 47%, not 31%. Okay, SODIS uses UV light to sterilize water. Okay, give 1 other method of sterilizing water. Okay, we could use chlorine. We haven't talked about this, but you could use ozone. Okay, so chlorine, that's the one we talked about in lessons. A student tested a seawater sample of dissolved salts. Okay, student tested seawater samples of dissolved salts. This apparatus, here we go. Look at this apparatus here. We've got a Bunsen burner, that's causing heat. Beaker, boiling water, the dissolved salts. Okay, the seawater's up here. Seawater's going to have salty water in it, isn't it? Salty water up there. What is apparatus X in figure 1? So we've got X here. Right, so that there is a watch glass. It's called a watch glass. Okay, next question. The student did a test 4 times. Let's make sure we prep it. So the student did the test 4 times. The student calculated the mass of the solid apparatus X on side X. The table below shows the student's results. Mass of solid in grams, 0.12, 0.29, 0.14, 0.15. I'm going to highlight that one. That seems a bit odd. Calculate the mean of the solid. Do not include the anomalous result. Do not include the anomalous result. So straight away we need to work out which one is anomalous. We're going to circle that one because it doesn't match the others. There must have been some kind of error in that one. Okay, can you give your answers? There's 2 significant figures. That's really key at the bottom in mass. Okay, so what we have to do, we do 0.12 plus 0.14 plus 0.15 times by 3. Sorry, not times by 3, divided by 3. And that brings us out as 0.14. So 2 significant figures. Okay, so 2 significant figures, it was 0.14. Okay, that's going to get you all 3 marks. There's 3 marks there for that question. Next question. The student distilled a sample of seawater in an apparatus shown below in figure 2. Here's figure 2. Seawater test tube. Heating. Okay, heat's going to heat the water's going to rise, going to go down there, and hopefully we're going to collect pure water in there. and the salt will be left behind in this conical flask. Okay, what change of state is happening at the surface of the seawater? Okay, at the surface of the seawater in this section here. So what change of state is going on there? Now, they specifically said at the surface. Okay, at the surface, so we're going to say evaporation at this point. Boiling happens all throughout, so when they specifically mention surface, it's evaporation. Okay, describe how the water in the test tube in figure 2 is different from seawater. Okay, so the test tube will have no more salt in it. Okay, because we could say this is pure. It's got no salt. That's enough for 2 marks. Okay, pure, no salt. And why it's enough for 2 marks? Sorry, enough for 1 mark. We're saying it's pure because the water's come up here. The salt is being left behind. Okay, because the water and the salt have different boiling points. The water has a lower boiling point, so the water boils at 100 degrees C, where salt doesn't. So salt will not turn into a gas and will not move with the water up and over this way. And then the water cools down, and what you collect in here is pure water. Okay, now that's pure water, not potable water. Why does producing drinking water from seawater using distillation cost a lot of money? Well, it costs a lot of money to heat it. Okay, heating water to, remember we have to boil it, so 100 degrees C, no, that's not degrees C, is costly. Okay, we could let it evaporate, that might take a really long time. Okay, all the way. River water is filtered, then sterilised to make drinking water. There are two processes done. Okay, filtering and sterilising. Why are the two? So why do we filter? So we filter it to remove bits. Okay, remove particles. Okay, we're going to remove the particles. And why do we sterilise it? That's going to kill any microbes. Okay, because potable water is free of bits, but also free of these microbes, bacteria and fungi. Okay, so remove particles, kill the microbes, those yucky microbes. We often use, so in drinking water that we have chlorine in our water. That kills the microbes. Okay, next question. Used disposable nappies are sent to landfill. Okay, 1,600,000 babies in the UK use disposable nappies. Each baby uses 5 nappies in every day. Calculate the total number of disposable nappies in 1 day. So 5 nappies per day, and we've got 1,600,000 babies. We're going to leave this in standard form. That's one of the maths things that we used at the beginning of the term. So we need to remember it's times 10 to the power of. So we've got 1,600,000 times that by 5. So that is 8 million. Okay, so that takes 8 million. And then what we need to do, we need to turn that into standard form. So remember, we've got 1, 2, 3, 4, 5, 6. So it's 8 times 10 to the power of 6. And that's the number of nappies. 8 times 10 to the power of 6. Standard form is like that. Okay, because there are 1, 2, 3, 4, 5, 6. So we times it by 10 6 times. Times by 10 would be 80. Times by 10 twice, 800. Times by 10 3 times, 4, 5, 6 times. Okay, next question. Disposable nappies contain hydrogel. A hydrogel is a substance that absorbs water. A nappy manufacturer investigated the mass of water absorbed by different material hydrogel. Table 1 shows the results. Okay, we've got the mass of hydrogel in grams down here. We've got experiment 1, experiment 2, experiment 3, and then we've got an average. Okay, this is obviously we're going increasing the mass of the hydrogel. Experiment 1, we're seeing an increase in mass absorbed, decrease in mass absorbed, decrease in mass absorbed. Okay, the mean mass in X. Which of the results of 1.5 grams of hydrogel is anomalous? So 1.5 grams, we need to look at on this one here. And we know that this is 450, 450. They're similar, so the one that's out is 500, so we're going to say experiment 3. Okay, experiment 3. Calculate the value of X in table 1. We do 148 plus 151 plus 151, that's a plus 151 divided by 3. Do that bit first. Okay, and it comes out at 150 grams. Some of the results shown below in the graph. Mean water absorbed in grams, the mass of hydrogel in grams. We're seeing this direct fit here, so we got a directly proportional graph as it goes to origin. Determine the mass of the water absorbed at 1.8. So what we need to do is we need to find 5, 6, 7, 8, 9, 10. So every little square equals 0.1. So we need to go 3 squares up from this side, 1, 2, 3, and we find it reaches there. That's 3 squares across. Okay, and that if we look down there, that is 2 squares down. So that's 2 squares down. So we've got this one, we've got 400, 420, 40, 60, 85. Okay, so 4s, these goes in 40, 4, 8, 12. So that's 120. So that's 520. Okay, so but let's have a little double check. That's maybe just slightly past the second one. So 520 to that line plus a little bit. So let's say 530 grams to be sure. Okay. Next question. Which of the following is a valid conclusion for the graph? Okay, tick 1. We're going to say mean mass of water absorbed in grams. So we start with the sign. It's either equal to, it's either directly proportional to, equal to, less than, or this one. So I've already said that it's proportional to. So it's going to be that one there. That means proportional. This signal here means proportional to. Okay. Fabric nappies are alternative to disposable nappies. Nappy 2 shows information on the life cycle assessment of fabric nappies. Okay, LCAs, that's our understanding of LCAs coming in here. Compare the advantages and disadvantages of fabric nappies instead of disposable nappies. Okay, look at table 2. We can see that fabric nappies are biodegradable, that they are reusable, not. Okay, carbon dioxide, more carbon dioxide dose, it's a bad thing. And then this one, more water to clean them. So they're positives for those, and these are the positives for the fabric nappy. So compare the advantages and disadvantages. Okay, so we're going to say advantages are reusable and biodegradable. Disadvantages is they use more CO2, okay, per nappy, and lots more water. Okay, so when we're thinking about which one do we believe is actually better for the environment, looking at this table, I'd say that generating more carbon dioxide and using more water is a bad thing for the environment. So the fact that they're biodegradable is a positive. So what do we do with these ones? It causes landfill issues. So this is a landfill problem, where this is an environmental problem. Okay, so we need to be really careful on that one. Apparatus below, we're looking at potable water again. We're heating up water, AWB. So which apparatus W? So which apparatus is W? So let's have a look at W. Okay, this is a special flask. Okay, which we call it a round bottom flask. There's a flask there. And next question. What is the name of the method of separation? Well, this one is distillation. Okay, this one is distillation. It is back to the fractional distillation. The name of the change of the state taking place A and B in the figure above. Use the word change of state at A. So let's have a look. Change of state in A. We've got boiling or evaporation. So we've got boiling here. Okay, and then it says at B, let's find where B is. B is here, so this is going back down, so this is condensation. Okay, condensing. Because that was a liquid to a gas, boiling. This is a gas to a liquid, condensing. Okay, next question. Table 1 shows the boiling points of hydrocarbons in the fuel. We got 36, 69, 98, 125. Which hydrocarbon is the last to collect in the beaker? Okay, remembering that a higher boiling point is going to be one that comes out last. Okay, so the one that's the highest boiling point comes out last. So that must be octane. Let's move it on. The fuel in the mixture of liquids has been designed as a useful product. Write the name given to this type of mixture. Okay, the fuel in the mixture of liquid has been given a design as a useful product. Name of the type of mixture. Okay, it is a formulation. Describe how the fuel is different from crude oil. Describe how the fuel it has got less. It's not a mixture. It is pure. It is a pure compound. Okay, formulation is a pure compound. It's got exactly the amount of stuff that we think, and we know the exact amounts. That makes it a formulation. Whereas crude oil, it's just got a random selection of this, that, and the other in no specific amounts. Okay, where a formulation, when we got an exact amount of what we want, that is a pure compound. Okay. A student measured the melting point of a solid hydrocarbon 4 times. 1, 2, 3, 4. Okay. Calculate the mean of the hydrocarbon, leaving out any anomalous results. 37, 37, 35, 48. Leave out trial 2. So we need to do 35 plus 37 plus 37 divided by 3. 35, 37, 37 divided by 3 is 36.33. 36.33. Okay, it asks us 2 significant figures, so we're going to get rid of those 2 there. So our answer is 36. Okay, so that's our answer there. Make sure we do that correct. Name 2 methods of treating potable water. So the 2 methods that we're going to think about. Okay, desalination and sterilization. Okay, sterilizing. They're the 2 that, so name 2 methods, so that means we need to tick 2 boxes. Always make sure you read that and don't just tick 1 or tick more than that. Every one you do extra is going to lose you some marks. Okay, next question. We've got mass in milligrams per decimeters cubed, Cl minus, Na plus, NO3 plus. Okay, we've got these ones here. What is the name of the ion? Cl minus. Cl minus, this ion. Cl minus, Cl is chlorine. Okay, so it's a chlorine, but chlorine is not a name of an ion, so it's chloride. Okay, chlorine is the name of the compound, chloride is the name of the ion. Okay, use the information on the table above to pick the bar chart, figure 1. We need the NO3 minus, we've got to go to 40. So, what's the things? 5, 10, 15, 20, so each one's 5. 5, 10, 15, 20, 25, 30, 35. So 25's there, 30, 35, 40. Make sure we go up the right amount, and it's got to be in the same place. Now, mine's not very neat there, but it needs to be 1 bar away and only 1 bar long. Okay? 1 bar away, 1 bar long, and each one of these is 5s. 5, 10, 15, 25, 30, 35, 40. Okay? 25, 30, 35, 3 up from there. 1, 2, 3, up from there. Okay? Check that really carefully. Look at the questions labelled A, B, C, D. Okay? How many substances are in drinking water? How much fluoride in drinking water? Is fluoride soluble in drinking water? Should fluoride be added to drinking water? Which of these questions cannot be answered by science alone? Which one of these cannot be answered by science alone? Should fluoride be added to drinking water? This one is not just about science, it's about people's opinions. Okay? Give 2 reasons why the answer you have chosen cannot be answered by science alone. Okay? People have the right to choose. People might have the right to choose. Is it ethical? What about the things it might be killing in the future, etc.? Okay. Next question. A sample of drinking water contains 1.5 milligrams of fluoride per decimeter cubed of water. The person drinks 1 decimeter cubed of this water. The recommended daily amount is 4.0 milligrams. Which calculation gives the percentage recommended daily of fluoride in decimeters cubed? Okay, well, we must do 1.5. Okay, 1.5, and then we've got divided by 4.0 times that by 100. Okay, and let's see what that one is. 1.5 over 4.0 times that, so it's that first one there. Okay, figure 2 shows the effect of fluoride in drinking water on tooth decay in different age groups. Okay, water with fluoride, water without fluoride. Percentage of teeth showing decay. So it's in every age group. There's more people showing decay without fluoride. Describe the pattern. So we're saying without fluoride. Shows more decay, and that increases with age. So for 2 marks, we've also saying without fluoride shows more decay, and then that increases with age. And last but not least, describe the effect of adding fluoride to drinking water for the age groups in figure 2. It reduces tooth decay. And that effect is greater the older you are. But that might have something to do with using it for longer. Okay? And we're done.